Okay, so thank you. This is the third lecture. I will talk about cosmic microgravity anisotropies and more parameters. Okay, so let's review what we learned from lecture number 2. We learned that the standard cosmological model is based on several assumptions: general relativity, inflation, cold dark matter, the possibility of this cosmological constant. And if you do this kind of assumption, then you have a theoretical model, and this theoretical model can fit very well the observation by varying only 6 parameters. So the minimal model, okay, if you want to mimic supersymmetry, the minimal cosmological model has 6 parameters. And assuming inflation, we assume a flat universe. So these parameters are the Hubble constant, the baryon and cold dark matter density, the amplitude and the spectral index of this primordial scalar inflation and perturbation, and this optical depth tau, which condensate all the information about this reionization process. Okay. Now, we saw that W07 and other recent cosmic microground experiments can put strong and good constraints on all these 6 parameters. However, for example, if you remove some of the assumptions on how we treat reionization, then this can affect the cosmological parameters, and you have, for example, a different value for the spectral index. Okay. So one should be aware that this model is based on these very important assumptions, okay, but you also have astrophysical assumptions. Okay. We saw that a major assumption is that this dark energy component is made of a cosmological constant. Cosmological constant is an enormous problem from a theoretical point of view, and we saw that if we move to a simple cosmological constant, which is just a component which is constant without perturbations, to another simple model but with an equation of state that varies with redshift, then the cosmic microground constraints can change, especially on the Hubble parameter and the matter density. We saw in practice that with a CMB we don't really measure W, okay, and the cosmic microground is not sensitive to dark energy perturbation if we assume a model where W is constant. However, the model of dark energy are more complicated, more complex, okay, so we can have an evolution with redshift of W. We might have a contribution of that dark energy also in the early epochs at the recombination, and so in this case, for this kind of models, the cosmic microground can provide a very important information. Okay, so in this lecture what we try to understand is from this 6 parameter model, how many other parameters I can consider, okay? So let's look at all the parameters, and all the possible extension of this standard model of structure formation. So we already saw dark energy, and we already saw that changing the from cosmological constant to dark energy has important implication. We briefly saw the effect of reionization. I don't have time to speak about inflation. I point you to the lecture by the leader of the cosmology on the beach of the last year school, okay, if you want to look at inflation. Especially, the point is the following: at the moment I'm only assuming a scalar perturbation. What happens if I have a tensor perturbation? Okay, what kind of constraint I have for tensor perturbation? And an important, very important point is the following: that if you really want to falsify inflation, the only way I know is to detect vector perturbation. Okay? So this is a crucial point, because if inflation is correct, then we should not see at all this vector perturbation. They should not be relevant. Okay, something that is very interesting is the problem of primordial condition. Okay, inflation generally predicts adiabatic primordial conditions, but we can, in some way, have a mixture of adiabatic and isosurfacial modes. So the idea is, okay, instead of considering all adiabatic initial conditions, let's consider all the possible initial conditions, okay, that I have. What kind of effect I will have on my constraints. Another extension is by including a neutrino mass, okay? So let's try to include a neutrino mass. But how many neutrino I should include? 3? Okay? But what about if I have another light particle? What about if I have a light axion? Okay? So we can extend also in this direction, in the direction of the hot dark matter component. Then we spoke about the ionization, but we might in some way have other mechanisms that can affect the recombination process. The first simple effect is the helium abundance. Helium is present at the combination. What is the amount of helium we have in the universe? It's 24%, 25, 23, okay? What is this effect? And not only, but at the combination, we saw, for example, that we might have an injection of extra relativistic particles, extra photons by dark matter annihilations or other processes. Okay. And finally, we can also look at possible variation of fundamental constants and modification of thermodynamics, etc., etc. Okay. So here, when I speak about dark energy, I also include here the possibility of modification to general relativity. Okay. Cosmic micro-round anisotropy should give you more or less the same information on dark energy or on modified gravity. Okay, so let's look at the general primordial cosmic perturbation. Because we saw that in practice we have this curvature perturbation, okay? And we might have this curvature perturbation, but we have also an entropy, we might have entropy perturbation, okay? So curvature perturbations are defined as a diabatic perturbation, and entropy perturbation are usually called as isocurvature perturbation. Okay. This perturbation is quantified by the entropy perturbation. Okay. And you can have this difference here between the delta rho x divided by rho x plus px minus delta rho gamma divided by rho gamma plus p gamma. In the case, of course, of baryons called dark matter, but you may have also isocurvature modes where you have this perturbation in a neutrino, okay, and in neutrino densities and in neutrino momentum. Okay. So in practice, you don't have only a adiabatic initial condition, but you have only neutrino isocurvature velocity initial condition, baryonic isocurvature initial condition, neutrino isocurvature density perturbation. Okay. So in practice, at the end, you have something like 5 possible ways for having these initial conditions. I point to this interesting paper by Fugger in 2000. And you might have also correlation with these 5 modes. Okay? So you have a 5 plus 10 is 15. 15 more parameters. Not only 15 more parameters, but each mode can have a different spectral index. Okay? So you go to 20 parameters. Then you can also add all the other cosmological parameters, so you arrive at 30 parameters. Okay, it's the usual story. We saw that for fitting an elephant I need 15 parameters. Now I have 30 parameters. With 30 parameters I can fit an elephant surfing. Okay? I mean, more or less now we are going to a level that I can do anything. So if we don't assume any physical model in reality, if we say, okay, let's look at the most general initial perturbation, then what happens is what we expect, that we lose any constraint in practice. So I point you 2 papers that in my opinion are quite interesting. One is by Cavi Moodley in 2004 and the other by Joe Dunkley in 2005. Here, Cavi, what he did was to fix the fact that the universe was flat. And you can see here that the main effect, I'm sorry, it's not really correct, but you see the main effect is on the baryon density. You have that the baryon density is practically 0.02 here, and if you add this isocurvature mode, it's 0.04. Okay, so you double the uncertainty, you double the value, okay, on the baryon density. So you lose any information on the baryon density if you assume flatness. But if you don't assume flatness, okay, you can see here the effect that the CMB data alone, I told you, doesn't measure really, this is the adiabatic case, okay. CMB alone doesn't really measure the curvature, but if you put a prior on the Hubble parameter, you say I want the Hubble parameter to be larger than 0.5, then you see you recover this value, the curvature of the universe from W map 5, I think, this is, or W map 3, I think, is 1 plus minus 1.03 plus minus 3%. Okay? This is in case of adiabatic, but then if you add all these possible general perturbations, you see here, okay, you change the value of bonding curvature from 1.1 plus minus 5%. It's not a big difference, okay? But for example, if you do put the prior, you should compare 1.2, 1.6. Okay? So there is a strong effect from this general primordial cosmic perturbation. The problem is, okay, should we really care about this? Should we always run 20, 25 parameters more each time we run our Cosmo MC? What we should do? Usually what we do is at most, at least if you look at the recent paper by W7, to consider two models and to consider a single additional isoturbature mode. So in practice, your total angular power spectrum is of this form. You have your total CL, you have the adiabatic term here, plus the isoturbature term here. You have this alpha. Alpha is the relative amount of adiabatic and isoturbature mode, plus the correlation. But we know in some model that these adiabatic and isoturbature are totally anti-correlated, so this beta is -1. And in other models, beta is 0, you don't have any correlation. So you put actually a constraint just on this single parameter alpha, and we call alpha -1 when we look at the curvature model, so here is beta -1, or we go with 0. Okay, and these are the current constraints. 1%, 10%. Okay? Of course, when you add this correlation, it seems that you have a stronger bound. Okay? So if you go in the literature, you look at the WMAP paper, what we do at the moment is say, okay, let's consider at the beginning just a model with one single parameter. And let's see if this single parameter is different from 0, or we put just another limit. Okay? Okay, so this is a way to analyze this data set. So you include parameters, okay, in blindly. But another possibility is to start and to look what I can define as laboratory parameters. These are very interesting in my opinion, because these laboratory parameters can be measured in an independent and independent way and directly. Okay. So I explained the point. These parameters are, for example, the neutrino mass, the neutrino effective number, the primordial helium, and the fundamental constant. So we saw previously that we can constrain probably dark energy. We can have information on inflation from this cosmological data. But the problem is, okay, imagine that I have this dark energy, constraint in dark energy. Imagine I have a future evidence on dark energy. I want a confirmation in the laboratory. Okay? Can I do this? It's practically impossible. Okay? We cannot test inflation or dark energy in the laboratory. It's really, unless you have some very nice idea. Okay? Or in some cases. But on the other hand, we have these parameters that we can constrain with cosmology, and that at the same time we can constrain the laboratory experiments, or looking, for example, at the abundance of helium in the universe. Okay? So this is a very important point because we can establish a clear connection, okay, and we can really check the model. Okay? So imagine that the future experiment will measure the neutrino mass, and that this value will be different from what we get from cosmology, then it means something is wrong, that in cosmology we miss something. Okay? So this is the reason why I think these parameters are important. So let's start with the helium abundance. The effect of helium abundance is changing the combination process, okay, at high redshift. And there is an effect on the cosmic microwave anisotropies. Here you can see the plot, two models. One model with 1% of helium abundance, another model with 24% of helium abundance. Okay? You see the difference. So you see a difference on very small scale because recombination of helium takes place at higher redshift with respect to the recombination of hydrogen. Okay? So if you measure this damping tail, you get information on the helium abundance. Okay, what is the current status of these constraints? WMAP plus ACT gives you this constraint, 0.313 plus minus 4%, 5%. Okay? So this result is great because it's telling you that actually we need helium to constrain, to explain the observation made by Hart. Okay? So it's a detection of helium, primordial helium through cosmology, which is very interesting in my opinion. And you can see that you can have only if you add act to WMAP. With WMAP only, these are the likelihood plots, you don't have a clear detection of this helium. If you add this act data, measure the small scale anisotropy, you have this value. Okay, let's compare this value with direct measurements, and things are more or less consistent. Okay. But the point is that these direct measurements, which are very recent, are a little bit higher than what we expect from standard BBM nucleosynthesis and assuming the biodensity from WMAP. Okay. So there is a small tension here. It's not clear, okay? We don't want to say anything, but there is this tension. So the helium abundance in the standard BBM using the baryon density from WMAP is slightly smaller. Okay. It is a point. Now let's go to neutrinos. We have plenty of neutrinos in the standard cosmological model. They decouple from the primordial plasma temperature of about 1 MeV. We should have this neutrino background around us, the temperature of about 10 to the minus 4 eV, with this kind of density, numerical density. Now this in the case of the relativistic neutrino, but if you add a small neutrino mass, okay, you have this very interesting relation between the energy density in massive neutrino and the mass of the 3 neutrinos. Okay. With this relation is very interesting because cosmology changes if you vary this quantity here, so we can constrain this quantity. And by getting this relation, we can put bounds or hopefully detect the neutrino mass using cosmology. Okay, first of all, let's assume a relativistic neutrino. Okay, we have this relativistic neutrino background. What kind of effect we should expect on the cosmic micro background? The idea is to use cosmic micro background anisotropies to constrain neutrino background. May sound quite strange, but the point is that also neutrinos are heavy, also the neutrinos have an effect, and they are acting here, okay, in the so-called integrated Sachs-Wolf effect at early times. Because neutrinos are relativistic, they change the relativistic component, you have variation in the potential, time variation, so you have this term here that varies if you change the amount of neutrinos in the universe. So this is just the area SW. You can see from this plot, here with 3 neutrinos we expect this kind of cosmic CMB anisotropy. You move from 3 to 7 and you increase the anisotropy, the cosmic micro background, by increasing the energy density in the neutrino component. So this is what you expect, is the cosmic angular power spectrum. If you put 0 neutrino in your camp, and if you have 3 neutrinos, okay, you see this difference. You increase here thanks to the air integrated Sachs-Wolf effect, essentially. Okay? So the point, I don't know if you want to try this. If you do this, CAMB gives you an error because CAMB has a minimum 2 neutrinos. Okay, you have to just comment a line in CAMB if you want to have a spectrum. So there are papers where they say we modified the CAMB code to include a variation. It's just commenting a line, just in case. Okay.
There should be an effect on the neutrino masses in there, right?
I think the effect is minimal on this. You mean if I assume a neutrino mass here in this plot?
It matters whether at CMB decoupling, how relativistic are they? CMB decoupling, if they are heavier?
Yeah, but at the moment, I mean, the effect is I agree, but it's more. Okay, we don't see this here. Okay, anyway, so there is this effect, and this effect has been measured. Okay, if you take the WMAP5 results, they already found an evidence at more than 95% confidence level for this neutrino background. You see, these are the light blues, the blue one is from WMAP5, this is the 3 neutrino model, okay? And you see 0 is excluded at more than 2 sigma. So this is quite interesting and nice, because we are starting to see neutrinos through CMB anisotropies. But let's see if we can do something more. Something interesting is the following. I think Ed Betchinger mentioned this yesterday, that if you have neutrinos, they are not a perfect fluid, they have a shear component. Okay? So can we, let's go back, this is the transparency I showed the first day, okay? These are the equations that you have to integrate to compute the angular power spectrum of the CMB anisotropies. So you have these neutrinos, and these neutrinos are not a perfect fluid, you see? You have a hierarchy of equations exactly like photons, but without interactions, okay? So the point is that you have these terms here. So the neutrinos are imperfect fluid, they are relativistic, so there is a shear component. Can we measure this shear component? Can we measure the anisotropies in the neutrino background? So imagine you have this cosmic neutrino background, now you have a huge detector, and you try to measure the anisotropies in the neutrino background, okay? I mean, it's impossible to measure actually the neutrino background, now we are thinking about the anisotropies in the neutrino background. Now, you can compute this theoretically, as been done, for example, by Wayne et al. In this paper. And this is the angular power spectrum of the neutrino anisotropies. Okay? And cosmology of the beach 3000, I think they probably start to show some data points here, but for the moment we cannot really use this. Okay? Of course, Axel will be there. Anyway, the point is that there is an effect on the CMB anisotropy. If you include or not anisotropies in the neutrino background, okay? So this is just gives you the idea of the effect by considering the neutrino background as a fluid, this is wrong, or by solving the hierarchy of the Boltzmann equation, okay? So there is an effect. And the idea, can we measure this effect? Can we measure this shear component in the neutrino background? We can do this by introducing this parameter, that is the viscosity, okay, which actually the effect of this parameter is just to cut away the hierarchy, to stop the integration of the hierarchy equation to the first two equations, okay? So in practice, if you have a 0, you don't have anisotropies, okay? You have a fluid. If you have a 1 over square root of 3, then you have these anisotropies. So the idea is now I have this additional parameter, I do the analysis, and I see what is the value of this parameter. If this parameter is larger than 0, in some way I detected these anisotropies in the neutrino background. And this is the result, okay? And actually, with W map 1 and SLOAN, okay, because there is a degeneracy between these anisotropies and the scalar petal index, you can have an indication at about 2 sigma, okay, for these anisotropies. So this is important because, as Betchinger said, we are looking at this radiation component in the universe. Okay, so anisotropies is something that is really related to neutrino, but we may have, for example, a scalar field or something different. Okay, so in this way we are still checking, okay, the model. Okay, there will be another analysis. I think I can skip here. And let's move to some other interesting connection of neutrino physics. The interesting connection is the following, that when you change the neutrino number, okay, so now the idea is different. Before I wanted to detect this neutrino anisotropy, the neutrino background. Now I'm saying, but I'm sure that I have 3 neutrino in the universe. Maybe I can have an extra neutrino background, okay? And what are the implications of having extra relativistic particles in the universe in the estimation of the cosmological parameters? And you can see here that you have a degeneracies, and one of the most important degeneracies is with the age of the universe. Reality is with the Hubble constant. So you can see here the constraints from WMAP and other cosmic microgram experiments. Here is the age of the universe, here's the number of neutrino. Okay? So you can see that you have that the plot close here, okay? So you have a detection of the neutrino background, But you can see that you might have also 8 neutrinos in the universe, and you are still compatible with CMB data, but the age of the universe will be at about 11 million years, will be drastically different. Okay. Now, why this is important? Because one of the strong claims from the WMAP collaboration at the beginning was a precise measurement of the age of the universe using WMAP. So in this plot you have a determination of the age of the universe at different redshift from astrophysical objects, and this blue line is the constraint from WMAP, okay, assuming a standard model. So they claim that the age of the universe is 13.8 plus minus 0.2 gigayears, okay? So it's a very precise measurement. It's one of the most precise measured parameters from WMAP. And so you can see here these data points that are coming from direct observations, okay? The error bars here are much larger, okay? So you can say, okay, I don't want to know anymore anything about the age of the universe from astrophysical objects. I have this measurement from WMAP, so who cares? The point is that this measurement is model dependent. If you change, if you include a W, okay, you see the constraint doesn't change much. There is just a 30% change in the error bars. But if you now do the analysis by saying, actually, don't know how many neutrinos I have in the universe, the results change, okay? Now your results is from WMAP 13.8 plus minus 2 or 3 gigayears. And if you compare with the previous data points, you see now you have the 68 and 95% confidence level, which are much larger, okay? So now this gives you two information. First of all, that you should not believe, okay, the constraint coming from CMB are always model dependent, okay? So any kind of complementary information is always extremely helpful. And second, now I can use these data points and include these data points in my analysis to constrain the age of the universe and to have a better constraint on the neutrino. Okay? So I can use this astrophysical object to constrain the neutrino number plus cosmology. And this is the result we got in this paper with Francesco De Bernardis, Licia, and Raul. And of course, Licia will answer all the questions about this paper. But anyway, we got this result that the number of neutrino is 3.7 plus minus 1.1 at 95% confidence level. Okay? Which is, in my opinion, a very nice result. Of course. Okay, so this is a point. But the nice thing here, the interesting thing about the neutrino number, okay, let's go back. You see here, this is 3.7. It's not 3. Okay? It seems like there is something more. It seems like we are more than 3 neutrinos. And if you go and look at the most recent results from WMAP, okay, you see that the constraint of the neutrino is 4.4 plus 1.5, a 95% confidence level. It seems like 3 is starting to be excluded at the level of 2 sigma. Okay? So it seems that cosmology is suggesting, okay, we should be really careful at the moment, that we have 4 neutrinos instead of 3. This is quite interesting. I mean, you can see there are other papers in the past, okay? You see always, this is the standard model, and the number of neutrinos is always larger, okay, than what expected from cosmological data. This is the recent result by Hamann et al. They pointed in the PRL paper, okay, a few months ago. And you see here, this is the additional neutrino, okay, that the likelihoods are preferring this additional 1 or 2 neutrinos more than what you expect. And if you look at the most recent result from ACT gives you 5.3 plus minus 1.3. Okay? This is something we have really to understand. Something that the next data coming from Planck, for example, will solve. But there is the possibility of having more neutrinos than expected. So what about the neutrino mass?
Alessandro?
Yes.
When you say neutrino, basically means any relativity point.
it means this, yes. Any relativistic particles not interacting with matter, okay? Only gravitation interaction, okay? So what about the neutrino mass? I can go quick about this, but the point is that measuring the neutrino mass in laboratory is extremely difficult. And as you probably know, a way to measure the neutrino mass is by the beta decay. And the current bounce on one single species is about 2 electron volt to sigma. Okay? So if you ask yourself, okay, what kind of bounce we have in the laboratory on the neutrino mass, okay, the sum of nu is bound to be less than 6 electron volt, I think. Okay, it's conservative. Do you agree with this? Do you agree? No. More or less it's 6 electron volt. Okay. And there have been claims of neutrino mass in the past, but these claims are highly controversial from the members of the Helium Moscow experiment, which is using a neutrino-less double beta decay experiment. And they put these bounds, okay, on the m beta beta. So this is again, if you want to compare this with the sum of neutrino mass in cosmology, you have practically to multiply it by 3. Okay. So you say that they detect a neutrino with a mass which is between 0.4 and 1.5 eV. Okay. This is very controversial. This has to be tested. In general, what we know from laboratory experiments is that neutrino have mass because we measure these oscillations. And what we measure actually is the mass difference between these neutrino mass eigenstates. But I show you here 3 possible configurations which are in perfect agreement with all current neutrino data. So for example, you have your neutrino eigenstates like this, which is so-called the normal hierarchy, neutrino 1, neutrino 2, neutrino 3, but you might have a neutrino mass of neutrino 1 is slightly smaller than mass of neutrino 2, okay, which are both larger than mass of neutrino 3. This is called inverted hierarchy. Or we might have that the mass of these 3 species is much, much larger than the largest mass difference. Okay? These are 3 possible configurations which are compatible with laboratory experiments. Okay? So in practice, what I'm saying is that from laboratory experiments, we don't have a direct detection of the absolute neutrino mass scale. So if we want to test the neutrino hierarchy, we need an experiment, cosmological experiment, that goes down to these values. Okay? So if you want to test the degenerate hierarchy, you should have a measurement of the sum of the neutrino mass below 0.15 eV. If you want to test the inverted hierarchy, you should go down below 0.1 eV. And if you like to test the normal hierarchy, you should go down 0.05 eV. Let's say that if you go down this value, you for sure measure the neutrino mass, okay? If the standard 3 neutrino Faro picture is correct. Okay, so what about the current status of observation of, oops, sorry, this is not Maria's talk, she's not here. Anyway, what you can see here from this plot is that the current bounds you have three possible bounds, okay? Let's say, take the cosmological data, take only cosmic microgram data. If you take cosmic microgram data alone, you have an upper limit on the sum of neutrino mass of about 1.3 electron volt, which is already a very interesting result. It's already a fact. You say you have to compare this 1.3 with 6, okay? So it's 6 times better than what we get from beta decay. But you can add also other information, like information on the Hubble parameter, and you go down to 0.7 or 0.5. If you start to include all the data, including the large scale structure, and so, I mean, here systematics might be a little bit more important, you can go down to 0.3 electron volt. So the current best upper limit is less than 0.3 electron volt. Okay, 0.2, for example, this paper, recent paper that is pushing this limit to below 0.28 electron volt, but it's really taking everything together. So at the moment we don't have any indication, okay, we cannot really test the hierarchy, but the bounds are impressive. And it means that in few years, thanks for example with Planck, we can really start, okay, in having the correct sensitivity to test the hierarchy. Okay, so how many minutes do you have? 25. Okay. Do you agree with that? You didn't fall asleep. Okay, sure. Okay. So let's look at what kind of information we can get from Planck satellite. Okay, in the near future. Planck was launched the 14th of May 2009. Okay. Already in September, the Planck collaboration showed this very nice map of the CMB sky. Okay, this was the so-called Planck first light survey. Okay, that tells you that the experiment was working in a very nice way. And this is what the map that Chris showed you after 1 year. Okay, there is a very nice map of foregrounds. Okay, but we are interested in working in this small scale anisotrope and try to take information from these small anisotropes. So I want just to give you an idea of what kind of information, what kind of constraint we may get on these parameters in the very near future. So these are two plots showing you how Planck will improve with respect to W map on the angular power spectrum. Okay, the point is dead, but anyway, you can see clearly that you have a better, much better detection of the small angular scale. And if you remember what I said, you can expect that thanks to Planck, we have a much better determination of the helium abundance, okay, for example. And what we expect, more or less, this is a picture taken from the Planck book of a few years ago. But you can see what we expect as improvement on the several cosmological parameters. Okay, you have these, the blue contours are more or less from WMAP, and what we expect with Planck is to improve the constraints on all these parameters by a factor 4, 5. Okay, so if you take the standard model will be the constraint, the parameters of the standard model will be constrained in a better way by a factor 4, 5. Okay, this is what we also found in this paper, recent paper, where we forecast the ability of the Planck experiment of constraining these parameters, okay, which I call laboratory parameters. So in the case of a standard cosmological model, Planck will put this kind of constraint on these parameters. The point is that at the same time of the data release of Planck, there will be probably ACT-POL or other experiment, ground-based experiment. So we also look at the possibility of combining this data with this new ground-based experiment. And also, finally, we forecast the ability of this other future satellite experiment. There are several proposals around. One is American, another is European. The European is called CORE. Okay. And here you can see what kind of improvement you can have on these parameters if you use this additional data. Okay. So you see that Planck alone will have this constraint. If you use the most advanced ground-based data, we can improve by 1.5, okay, by 60%, okay, by 20% the constraint of these parameters. And if we go to the next satellite mission, we can improve by a factor 5 in some of the parameters and factor 2 in others. Okay. So it's just to tell you how well we can do with future experiments. But what about the helium abundance? Planck will put a 1% error on the helium abundance. Okay? Now I show you that the current constraint is about 5%, 6%. So Planck will improve by a factor 6. And so we start really, I don't want to say to be competitive with direct measurements, okay? But if the primordial abundance is 0.3, for sure Planck will detect this, okay? So we can rule out 0.24, let's say, respect to 0.26. Why is important? Because, as always, we compare with the BBN, big bang glucosynthesis. And if you want to increase the number of helium abundance in the primordial glucosynthesis, you have to change the neutrino abundance. Okay? So this is a very nice cross-check, because if we see that the helium abundance is larger, strongly larger than what predicted by BBN, then we have to solve this problem. Okay? And the nice thing is that with CMB-POL, with the future satellite experiment, we can be competitive with a direct measurement. Okay? So this is what really why I say that is important, because you can compare two numbers, the same thing, okay, with two numbers measured in a completely different way. Okay? And this is really important, in my opinion.
Sorry.
Yeah.
Maybe on your last slide, just show.
This one?
So, yeah, the way you probe helium, the helium abundance with the CMB is via its contributions to the baryonic density. Is that? I mean, you see a correlation here, right?
Yeah, this is a correlation because the effect is similar in the sense that the helium enters in the recombination change the relative amplitude of the peaks. Okay? And so in some way, you are changing recombination here, okay? And here you change the frequency of the oscillations, more or less. Okay? So there is I just plotting these two results. In reality, the physics I think is different. Okay, I might be wrong, but I think the physics of this, I mean, there is the degeneracy, but it comes from different physics. It might be interesting to check, but I'm not sure it's the same physics. Anyway, yeah, does that answer your question? Or more or less. Anyway, of course, the point is that we have to take this value, okay, from a W map, and this value from helium, and you know that BBN, you give an input the baryon density, and you have a value for Y, okay? So this is the reason why we are plotting these two parameters, because in the future, we have here a line like this coming, okay, if you want, from Big Bang to synthesis. And so we have to check. Okay, what about the neutrino number? The neutrino number, I think, will be a really, really interesting parameter to be measured from Planck. Because we expect to have a sensitivity of about 0.2. This means that if you have a 3, you can exclude 4 at 5 sigma. If you have a 4, you exclude 3 at 5 sigma. If you get 3.5, okay, you're very unlucky. But in some way, okay, there is enough sensitivity to the neutrino number, and so we can really solve this problem if the problem is there. Okay, if you believe the current data, you say, oh, this indication is enough for me, then Planck will give you an answer. And this is very important because if you have a 4 neutrino, then we have to change several things.
Excuse me.
Yeah.
And what happens if there are really 3 types of neutrino? Then what would you have to modify in the cosmology?
Nothing. Then you're okay. Actually, it's 3 point out. The interesting point is the following: that is not really 3. Okay, it's 3.04 because it depends on the decoupling. Okay. So the point is that you have a non-standard decoupling, and this non-standard decoupling, the neutrino decoupling model, can give you 3.1, for example, or 3.2, and these models can be tested by Planck plus ACT-Pol, for example. ACT-Pol is an example. Okay, it's just saying, okay, I take an experiment, ground-based experiment with this kind of sensitivity. And then you go down to 0.11. You see, with this fusion satellite experiment, you can go to 0.044. Okay? So you can check in principle the neutrino decoupling.
In case you have 4 or more, then you have to perhaps add like 4 charged lepton to the standard model part.
Maybe?
No?
No,
Charged lepton? No, charged.
No, these neutrinos are large, and you know from experiment that you have only 3 large neutrinos. So basically, I think because there's a misleading thing here with neutrinos. Neutrinos is perhaps not the right word of saying extra degrees, relativistic degrees of freedom, because people think of neutrinos. This is not necessarily neutrinos, it's just any relativistic body.
No, but in case there's a 4 neutrino,
No,
really
no.
Should be sterile.
Then you have to add perhaps a 4 or 5 charged lepton to the standard model.
There is no form neutrino in the standard model.
No,
Like
I know.
neutrino. There is not. There is not.
I know, but
Okay.
this.
Can this is the penultimate slide, okay? Change slide and then you discuss. Okay. Finally, I just want to remind you, okay, what are the limits we need to test the neutrino hierarchy for the mass, okay? And these are the constraints. So Planck will have an upper limit of about 0.2, okay? This is when you marginalize here, so it's 0.2, I think, at 2 sigma. Planck, with another experiment, will be 0.08, and CMB pole 0.05. So, in few words, let's say that if the hierarchy is degenerate, there are quite good chance for Planck to measure the neutrino mass. Okay. So in any case, it will be the best bound available neutrino mass you can have, okay, for a long time. Will be indirect, completely model dependent, but will be the best. And if you combine with other experiment, you might reach enough sensitivity to check the inverted hierarchy. Okay? So you don't only might completely rule out the degenerate hierarchy, but you might check the inverted hierarchy. So this is what I think is really important. Okay, so more or less this is why I think we need to still look at the parameters in the cosmic microground. Why? Okay, it's important to look for non-Gaussianities. It's important to look to other observables. But I think there is still enough information, interesting information, to be extracted from the cosmic microground isotropies. I told you that if you want to make put some constraints on dark energy, you have to combine with other cosmological observables. But then I show you these three cases, which these laboratory parameters. And if you want to constrain these parameters, you don't need other cosmological observables in principle. Okay, you can do everything by just using CMB. Okay, which is quite nice because you can reduce the importance of systematics. So I gave you these three examples: helium abundance, the neutrino number, and the neutrino mass. All these three things can be measured more or less in the future in laboratory. Okay, and I think it is very important. Anyway, this concludes my lecture, and I wish to thank you, Axel, and all of the organizers for this fantastic conference. I think you will have a competition next year, because I heard that in January 2012 there will be a school in cosmology in Romania, in Transylvania. So maybe you should be careful in choosing a very nice place. Okay, okay, thank you.
Okay, so we have plenty of time for questions, for discussion, remarks.
On this issue with the helium abundance, maybe more comment. That's a really interesting issue because you probe the helium abundance at different times. I mean, as you showed, you can probe it with the CMB alone, but you of course also probe it at BBN, Big Bang nucleosynthesis. And it will be very interesting, for example, if there is a mismatch. This delta N, this effective number of neutrinos that you get from at the BBN time might be different from the one that you get at the CMB time. Maybe it's 3 at BBN time and it's 4 at CMB time. So what would that tell you? That would tell you there is some physics beyond the standard model where you would generate after BBN some relativistic species, but that does not contribute to the entropy. And then you can start up building models, maybe saxions decaying into axions, and
I think you can also check all the physics of the neutrino decoupling. You can start to check this, which is really interesting. I mean, what kind of processes are okay? Because you asked a question before. Okay, I think all these tiny effects, okay, that we have in neutrino decoupling can be now investigated. And the non-standard models, non-standard models can be ruled out.
More questions?
So I have a similar question. You just mentioned that to constrain the mass of neutrinos, it's just enough to use CMB. But if the total mass is small, like 0.3 eV, like what you said, then after the combination, they become non-relativistic after the combination. So how can you? Okay,
I say that. Okay, I say that if you take the CMB, okay, and CMB means just the radiation. But the point is that between us there's a lensing. Okay, so you use the lensing signal. By using the lensing signal of the cosmic microgram, you improve. Planck will not really have a detection of the. I mean, we'll have a detection, but it will not really important. So you see the error bar is still at 0.4, 0.3 electron volts. By adding lensing information, you go down. So it's lensing it's the crucial observable. But it's lensing of the CMB, it's not lensing of the galaxies.
everybody's so shy. I was listening to the very interesting presentation by Alessandro, and at some point I had an idea, and let's see how weird it sounds. So thinking about this effect of the number of expected neutrinos species, okay? So I think if there's any students that is willing to skip the hot tub or has got a waterproof lato, may have a draft of the paper written, or beginning to be written by the beginning of the afternoon session.
A paper?
Yeah.
On what? Sorry.
Number of affected neutrino species. If you have a waterproof lato, come and talk to me.
This means I'm going to the hot tub.
It's not excluded. It will be a straightforward application of some of the exercise I told you to do in the statistical lectures, but it's too easy for postdocs. Sorry.
Thank you, nice. Yes.
I have a kind of comment. So I think that in the determination of the neutrino mass by cosmology, the imagination of the physicists is very big. So I remember a paper of Dodderson where they put the neutrinoless universe, when they put a coupling of the neutrino with a scalar field, and then the neutrino can decay, and then at this moment we will have any neutrino, background neutrino. So at the end, all these constraints on the neutrino mass will be taken with care.
Yeah, this is a possibility, but you see, interesting because if you couple the neutrino, then you reduce the shear component, and then you should not see shear in the cosmic microgram isotopy. So you see, the fact that we see the shear component in the CMB, so it's in some way an indication for anisotropies, it also constrains this kind of movement. It might also constrain, I think.
You take the higher helium abundance at face value or for neutrinos, if you worked out how you have to change the current understanding of primordial nucleosynthesis concentrations and the lithium-7 and so forth.
Okay, if you increase the neutrino number, you increase the lithium-7 for sure, but in order to be compatible with the measurement, I think you need 9 neutrinos or something like this, so no, I don't think it's viable. And the other question is if I put I think is compatible with 4, okay? So the choice is between 3 and 4, maybe 5 is the range. Okay.
More questions? How? Like 5 more minutes to ask. Okay, let's thank Anisotropies for his lecture.